Okay, let's get started. First item, the quizzes you guys took yesterday. The grades are posted in Genesis. I'm not going to release the questions with the answers just yet. I have a couple makeups that are being taken care of today. There was a little bit of a curve. Without the curve, one wrong was kind of extra painful. So I don't remember off the top of my head exactly what the curve was, but as soon as you see the scores and compare it to what's in Genesis, you'll understand. All right, so our next topic is we are graphing rational functions. This stuff in its basic form you should have covered in Algebra 2. Most of today should be review. Tomorrow and definitely, well, not tomorrow, Monday, and then Tuesday, Wednesday of next week, we will definitely be getting into some stuff that you would not have seen in Algebra 2. But the basics you should be relatively familiar with. The one side of the handout, I want to do a quick overview in terms of what's here in case you're looking for anything in particular. So the first set of notes right here on the top, those are a set of steps you can use, not necessarily that you have to do it in this exact order, but if you're looking for kind of for like that checklist of an efficient way to work your way through the problem, this is an efficient way to get the graph and identify the key features of the graph. All right, one of the important things that you have to do when you are graphing and finding the key features is identify the horizontal asymptotes if there are any. And we have very specific rules which are listed here, and we'll review them with the examples on the other side of the page. Now, instead of a horizontal asymptote, sometimes your graph has a slant asymptote. And this is one of the things that, depending on who you had for Algebra 2, you may or may not have seen. This talks about how you determine the equation for your slant asymptote. And then lastly, sometimes your graphs have holes in them, which are more formally known as removable discontinuities. This talks about how you determine what they are. So everything that's on this side of the page, we're going to review or go over either today or tomorrow with the examples on the other side of the page. So today what we're going to do is we're going to go over 1, 3, 4, 5, and 6. Tomorrow it's going to be a selection from the bottom part. I don't recall which numbers off the top of my head. But for the most part, today and Monday, I keep saying tomorrow. I'm not teaching this tomorrow. Today and Monday is kind of one big lesson. We're going to be using this handout for today and Monday. The homework that's posted in Google Classroom, which is the same homework that's on the board here in the physical classroom, that's the assignment for today and Monday. We're looking at the quiz on this stuff on Thursday, and I'll talk about expectations with the quiz in terms of some stuff you should know or not know as we work through the examples. I think that takes care of everything as far as background stuff goes. Any problems or questions before we get started? Okay. So for number 1, our function is 2x plus 1 over x plus 1. These are all the key features they're asking us to identify. And as we're identifying them, we're going to build the graph. Okay, your domain for the rational functions is going to be all real numbers except for when the bottom of the fraction is equal to 0. So the bottom of this fraction is equal to 0 when x is negative 1. So we're going to use the notation of x not equal to. This implies all real numbers, but you don't have to write out the all real numbers except. This is fine for that shorthand. Now, as long as this is in simplified form, that restriction in the domain is going to correspond to a vertical asymptote. Okay, the next place I'm going to go to is my intercepts. I'm skipping over range because we don't have nearly enough information to identify that. Okay, as long as this is in simplified form, which it is, your x-intercept is going to become from when the top of the fraction is equal to 0. And the reason why that works is x-intercept is when y is 0. When you set that equal to 0, the only way a fraction can be 0 is when the top of the fraction is 0. So the top of the fraction is 0 when x is negative 1/2. Y-intercept is when x is 0. When x is 0, that stuff drops out. You're left with 1 over 1. So your y-intercept is 1. All right, your horizontal asymptotes. They are determined by how the degree of the top relates to the degree of the bottom. The top is degree 1. The bottom is degree 1. Means they're the same degree. If the degrees are the same, your horizontal asymptote is going to be at the ratio of the lead coefficients, meaning 2 over 1. All right, the other possibilities are if the degree of the top is less than the degree of the bottom, y equals 0 is always your horizontal asymptote. And if the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. And those rules are on the other side of the page. A slant asymptote is going to occur if the degree of the top is exactly 1 more than the degree of the bottom, like a degree 2 over a degree 1. Okay, that's not going to happen in any of the examples we're doing today. We're not going to get to that until tomorrow. Monday. All right, all of these things that I've identified so far, you should be identifying without relying upon your graphing calculator. What you want to use the graphing calculator for is to flesh out the rest of this curve. Type it in your calculator, go to your table, get a couple points, flesh out the curve, and then once you see the graph, you can identify the range. All right, in the interest of time, I'm not going to graph all of these on the graphing calculator. We end up getting one branch up here and another branch down here. Now, you're not going to be physically graphing anything on an Edulastic quiz, but back in the day when things were more normal, what I would emphasize for a graph that would be on a quiz or test is making sure your asymptotes are located properly, make sure your intercepts are located properly, and then like a point or two on this branch, and you're probably not going to get anything meaningful on that branch. So those would be the things, the details I'd be looking for. But given our current situation, we're not going to have to worry about that right now. All right, now once you see the picture, whether it's what you drew or looking at your calculator screen, now you can identify the range. We're hitting all the y values below the horizontal asymptote, all the y values above the horizontal asymptote. So we're hitting all the y's except for at that horizontal asymptote at y is equal to 2. Good. All right, we're skipping over number 2. There's nothing that was overly interesting there that we're not going to address in one of the other examples. So we're going to hit 3. Now, for some of the things that we're identifying, it's nice to see it in polynomial form. And for some of the things we're identifying, it's nice to see it in factored form. So my personal preference is before I even start trying to figure stuff out, if appropriate, I'll write it both in polynomial form and in factored form. So domain is going to be all real numbers except for when the bottom of the fraction is equal to 0. So we have 2 restrictions in a domain. X can't equal positive 2 or negative 1. As long as that fraction is simplified, those restrictions will manifest themselves as vertical asymptotes. Okay, as long as this thing is simplified, your x-intercepts are going to be when the top of the fraction is equal to 0. If you have a 0 x-intercept, then that has to be the y-intercept as well. So we've got that point there. Horizontal asymptotes are determined by how the degree of the top relates to the degree of the bottom. With our first example, the degrees were the same. When they're the same, it's the ratio of the lead coefficient. Here, the degree of the top is less than the degree of the bottom. If the top is less than the bottom, y equals 0 is your horizontal asymptote. Okay, if you have a horizontal, you can't have a slant. The slant is going to happen when the degree of the top is exactly one more than the bottom, and that will be one of the variations we get to tomorrow. And all of this stuff that I've done so far, these are things that you should be pretty quickly and efficiently identifying without relying upon your graphing calculator. Okay, for the quiz, there are going to be two issues going on here. One of them, I specifically designed questions that you can't type in your graphing calculator. And I've made it long enough where if you're putting every single question into the graphing calculator, you're not going to finish. Okay, one of the skills is knowing what to use the calculator for and what not to use the calculator for. This stuff right here, you shouldn't be relying upon a calculator. Okay, what you should use a calculator for now is to flesh out the rest of this curve. So type it in, go to your table, grab some points, and then finish it up. So for this one here, we end up getting 3 branches. I forget the location. We get 1 branch down here. We get a second one in the middle doing this. And we get a third one out here. All right, so the next issue we need to talk about. Vertical asymptotes are never going to get crossed. Vertical asymptotes are like mathematical holy ground. They are never crossed under any circumstances whatsoever. Okay, horizontal asymptotes can be crossed relatively local to 0, but they don't get crossed at extreme values. So like out here, once you get sufficiently away from the origin, that isn't going to cross this. Once you get out here and you get significantly away from the origin, that won't cross that. But here it can. So that, in part, combining it together with the range, that middle branch actually hits all y values. We don't even have to look beyond that. That one little like cotangent looking wave in the middle hits all the y values. Good with 3? All right, number 4, the bottom is not factored. The part is partially factored. So I want to see it both ways. 1 completely multiplied out, 1 completely factored. So completely multiplied out, it would look like that. Completely factored, it would look like this. For some stuff we identify, it's nicer to look at this. For some stuff we identify, it's nicer to look at that. All right, domain, all real numbers except for when the bottom of the fraction is equal to 0. So we have two restrictions. X cannot equal positive 2 or negative 2. As long as this is in simplified form where it can't be reduced down to something else, those restrictions will manifest themselves as vertical asymptotes. If it does simplify down to something else, that's one of the variations we're going to talk about tomorrow. Okay, your intercepts for X, as long as the top, back it up a statement. X-intercepts, as long as this is in simplified form, it's going to be when the top of the fraction is equal to 0. So we have two X-intercepts plus and minus 3. If it simplifies down to something else, again, that's a variation we're going to talk about tomorrow. Okay, Y-intercept is when X is 0. When X is 0, that stuff drops out right there. You're left with negative 18 over negative 4. That reduces to positive 9 halves. So 0, 9 halves is your Y-intercept. 9 halves is 4.5. Right, horizontal asymptote. The top is degree 2. Bottom is degree 2. 2 is the same as 2. That means the degree of the top equals the degree of the bottom. Ratio of the lead coefficients. Y is equal to 2. If it has a horizontal asymptote, it can't have a slant. The ones that have the slant, that'll be one of the variations we get to tomorrow. All of this stuff you should be identifying without relying on a graphing calculator. What you want to use the graphing calculator for now is flesh out the rest of the curve. We end up getting 3 branches. In the middle, we get like a secant, cosecant looking U shape. Over here, we get one of these guys. Over here, we get one of these guys. All right, so when it comes to identifying the range, we got everything below that horizontal asymptote is being hit. And everything from that like vertex point up is getting hit. So if we're going to use interval notation, we want to think lower bound to upper bound. So the lower bound is negative infinity. It goes up to, but doesn't touch that horizontal asymptote. And you wouldn't know that unless you looked at the picture on your screen. So up to, but not including the 2. And then it includes that Y value of 9 halves up to positive infinity. Now, sometimes you just see the two things listed side by side like this. Sometimes they'll put the U in the middle for union. Either version is acceptable. I don't care what you do. Yes?
Can you explain how you got the Y-intercept?
That actual number of 9 halves.
You just plug in 0.
Yep. And now that drops out. Negative 18 over negative 4 reduces to 9 halves. All right. Anything else with number 4? All right, on to 5. So domain, all real numbers except for when the bottom of the fraction is equal to 0. That's never going to equal 0 in a real number system. If you try to set it equal to 0 and solve it, you end up taking the square root of a negative number, which means you have i's. So if you're trying to find when the bottom of the fraction is equal to 0 and it's producing i's, then there is no restriction in domain. It's all real numbers. Okay, if your domain is all real numbers, you can't possibly have a vertical asymptote. As long as this is simplified, which it is, x-intercept is going to be when the top of the fraction is equal to 0. 10x squared is 0, add 0. If 0 is an x-intercept, it must be the y-intercept. So far, that's what we got, a point. Not much to go on yet. All right, the horizontal asymptote. The degree of the top is 2. The degree of the bottom is 2. The degree of the top equals the degree of the bottom. It's the ratio of the lead coefficients. 10 over 2 or 5 halves. If you have a horizontal asymptote, you can't have a slant. Slant is when the degree of the top is exactly one more than the degree of the bottom. That's one of the variations we'll get to tomorrow. Okay, all of this stuff we've done so far, you should be doing this without relying upon your graphing calculator. Use your graphing calculator to flesh out the rest of the curve. We end up getting something that looks roughly like this. All right, so the range for the y values, the smallest y value is 0, and that is inclusive. And it goes up to, but doesn't touch the horizontal asymptote at 5 halves.
Because it doesn't touch 5 halves, is that why you
Exactly. Yeah, that means up to, but not including if you have the parenthesis. If you have the bracket, that means up to and including. Did I say that the right way? Parentheses up to and not including. Bracket is up to and including. Anything else with that one? All right, one more example for today. For number 6, we have 7x over 2x squared plus 1. Domain, all real numbers except for when the bottom of the fraction is equal to 0. That can never be 0. So your domain is all real numbers. If your domain is all real numbers, you can't possibly have a vertical asymptote. Or as long as this is simplified, the x-intercept is going to be when the top of the fraction is equal to 0. Top of the fraction 0, add 0. If you have an x-intercept, which is 0, your y-intercept has to be 0. So again, we got a point. All right, horizontal asymptote. That's determined by how the degree of the top compares to the degree of the bottom. The top is a degree 1, the bottom is a degree 2. The degree of the top is less than the degree of the bottom. If the top is less than the bottom, y equals 0. You can't have a slant asymptote and a horizontal asymptote in the same problem. So as soon as you identify a horizontal, you can't have a slant. The ones with the slant we're going to address Monday. All right. all of this stuff you should be identifying without relying upon a graphing calculator. What you want to use the graphing calculator for is to flesh this out. I'm not going to draw it to scale because it's a really smushed in graph here, but it has this basic shape to it. So in order to identify the range, we're going to have to get that maximum point and that minimum point down here. So that one I want to actually do. So I already have it typed in my calculator, 7x over 2x squared plus 1. And then when you graph it in a standard zoom window, it's kind of very smushed in towards the axes there. So I'll get that maximum point. And if we go 2 decimal places, that's at 0.71, about 2.47. And then get the minimum point. And that's about negative 0.71, negative 2.47. So the smallest y is the negative 2.47, and it includes it. It hits that point. The biggest y is the 2.47. Hits and includes that point. All right, I just want to use this example to remind you of a couple of things that we've talked about when we were doing trig graphing. We talked about it with the chapter 3 graphing. There's going to be an assignment next week that incorporates it back in. So in this neighborhood, we know that we're concave down. In this neighborhood, we know that we're concave up. Somewhere between concave up and concave down, there must be a point of inflection. So somewhere in here, we're going to hit point of inflection where it changes concavity. Now, for some problems, we could take a reasonably good guess. I think we could take more than a reasonably good guess. This curve appears to be perfectly symmetrical. So it'd be really safe to say 0, 0 is going to be a point of inflection. And it turns out it is. Now here, we're concave down, and then we switch to concave up. So we have another point of inflection out here somewhere, out there somewhere. I mean, we could take a guess, but it's nothing more than a guess. 0, 0, we can feel pretty good about. That, not so much. Okay, the other thing that we talked about in the same kind of topic of things was increasing, decreasing. We know for sure the graph is increasing from negative 0.71 to positive 0.71. We found that on the calculator. Then we know it's decreasing from there to there and decreasing from there to there. So that's going to be mixed into one of the assignments one of the days next week. I forget exactly when. But as long as we had this graph to look at, it was a good one to remind you of that stuff. Okay, also as a reminder of the bigger picture, in pre-calculus, we can find those mins and maxes by using a graphing calculator. In calculus, you'll be able to find those without relying upon a graphing calculator. You'll also be able to identify where it's increasing, where it's decreasing, where it's concave up, where it's concave down, where do you have points of inflection, just by looking at the equation and applying paper pencil skills to this. That will be a dividing line between what we can do here and what you'll be able to do next year. All right, that is it for today. Those of you that are at home, if you have any problems or questions, stay on and ask. Other than that, have a good weekend, and you guys can leave Google Meet.
Have a good weekend.
You too, thank you.